Hello, very good morning to everyone. So we are going to begin a brand new chapter, which is chapter 3 for chemical bonding. So I hope that you all will pay attention to this chapter because this chapter covers a lot of very important information that as a chemistry learner that you all might want to know. So without further ado, let's begin. So in these chapters, we are going to learn all about chemical bonding, including ionic bond, covalent bond, metallic bond. And then we also included intermolecular process, which is van der Waals and also hydrogen bonding. All right, so let's have a look at the periodic tables in here. Now, why is it important for you all to have a look at this periodic table is because the upcoming bonding that we are about to learn is something have to do with how do we classify the elements according to their metallic properties. Okay, so the one that I'm about to highlight are all metals. So as I described previously, so from here to here, all of them are metals. Okay, so you have from Group 1, Group 2, transition elements, some are Group 13, 14, 15, and 16s are also metals. And lanthanide series and actinide series, all of them are categorized as metals here. So I'm going to generally put it in this way, okay? So this is an interaction between metals and also non-metals. Okay, so I categorize this metalloid also part of the non-metal because they are after all, of course, they are not metals. So that is why I put it as a non-metals. Okay, so there is a very distinctive methods of how to determine what kind of bond, chemical bond will be formed in between elements in here. Okay, so the distinctive differences in between here is if let's say you have a reaction between metals and non-metals, you form a ionic bond. If it is an interaction between non-metal to non-metal, you form a covalent bond. And if it is in between metal and metal, you form metallic bond. Okay, so what is the difference between these three bonds here? So an ionic bond is to say that the electrostatic forces that holds the ions together in an ionic compound via electrostatic attraction forces, okay, between two oppositely charged ions, okay, between two oppositely charged ions. Whereas in the covalent bond, it is a bond in which two electrons are shared between two atoms. And then for a metallic bond, you shall have a bond that is formed between metal ions and a sea of delocalized electrons. Okay, right. So a Lewis dot and cross symbols of an element is often used to describe about its valence electrons. So generally, all group 1 will have one valence electron, right? All group 1 will have one valence electron, so you put one dot. All group 2 will have two valence electrons, so you put two dot. All group 13 has three valence electrons, you put three dot. All group 14 has four valence electrons, so you put four drops. All group 15 has the five valence electrons, so you put five dots. All group 16 have six valence electrons, you put six dots. And all group 17 has seven dots, put like this. And all group 18 has this one. So there is a special name for the uh, group 18 here. If for the case of the helium, we call them as a duplet. And for the case of the neon and also argon, we call them as an octet in here. Okay. So you can always use a dot and cross to represent the valence electrons inside an atom. So if let's say you want to draw boron in such way, it's also acceptable. What we do not accept is the weird symbols that you often see people using. For example, if you want to represent beryllium with a triangle, cannot. Okay, if you want to represent with this star, also cannot. If you love Naruto, Naruto have Sharingan, isn't it? draw like this. So that for boron you draw like this one, so it looks beautiful lah. Okay, then you draw one circle eyes. Okay, cannot. Okay, so it is not acceptable in Stpm. Okay, so you need accept dot and cross either like this, or like this. Can. Okay. So please do not simply use any dot and cross that you see from anywhere. Yeah. All right. So let's together learn the first bond, which is about ionic bonding. Right. So at the end of the lesson, you should be able to do the following things: explain the stability of ion based on noble gas configurations, half field orbitals, and also pseudo noble gas configuration. It's another terms for full field orbitals in here. And you also learn how to explain the formation of the ionic bonds in here. Okay. So how is ionic bond is formed? Let's have a look together. So an ionic bond is to describe as the electrostatic attraction forces that hold between oppositely charged ions together to form an ionic compounds in here. Okay, so technically, metals tends to form cation by donating electrons here. Okay, whereas non-metals tends to form an ion by accepting electrons here. So generally, we are going to say that Group 1, okay? Group 1 have one with the configuration of ns1 tends to donate one electrons in here, okay? So that you form Na plus, okay? So magnesium with two valence electrons in here tends to donate two electrons to form Mg2 plus in here. And then group 13 with three valence electrons, okay, will tends to donate three electrons to form Al3 plus in here. Whereas for nonmetals, all right, so group 15 tends to accept three electrons to form N3 minus in here. Group 16 tends to accept two electrons in here to form O2, for example, O2 minus here. Group 17 with the valence electron of number of valence electrons 7 here tends to accept electron to form F minus here. So no matter what these elements are doing, they are trying to achieve an octet configuration so that they are more stable in here. So the interactions comes in between the cation and anion that holds together via strong electrostatic attraction forces between the oppositely charged ions in here. Okay. So the key in here lies where how many electron donated, that will be how many electron accept. How many electrons donated by the metals will be how many electrons that is accepted. Okay, so to hold the key balance in here, so we often use the formula of A x plus, let's say we have ax plus by minus. So in order to achieve the balance in between the electron donate and accept, you multiply with lowest common multiple between x and y here. So by crossing in between both of them via the lowest common multiple, so that you have a y b x. Okay, and in here, since you uses A number of Y, you should have Y amount of A ions. Since you use X number of B, you should have X number of B ions in here. So if let's say you don't understand from the case, from the terms of A, X, B, Y, all are unknown. So let's have a look at by using the real examples in here. So if you have Na plus with N3 minus, so you put your 3 to this side, you put your Na to this side, so you form Na3N, 1, isn't it? So usually 1, we don't write 1, so we need to put the 1 here, okay? So another example, if you have Mg2 plus, we add with N3 minus, so you put the 2 at here, put the 3 at here, so that you form the formula of Mg3 and 2. See that? Okay, if Al3 plus and N3 minus, since they share neutral charge in here, so no need to no need to times 3 because lowest common multiple together in here is 3. So you have a formula ALN in here. Understand? Okay. So if let's say you want to represent by for Na plus and O2 minus. So we have Na plus and O2 minus. So switch here. So you have the formula of Na2O. Okay. If you have Mg2 plus and O2 minus, okay, therefore you have MgO. If you have Al3 plus and O2 minus, so you switch cross in between the symbols in here so that you have Al2O3 in here. Okay. And finally, if you have Na plus with F minus, so you form the formula of NaF. If you have Mg2 plus react with F2 minus, so you have MgF2. And if you have Al3 plus with F minus in here, so therefore you have AlF3. So with that, that is how you are going to represent the formula of the ionic compound that may be formed from the between the two oppositely charged ions in here. Okay, hope that you understand. Yeah. Okay, then let's have a look at a few more examples. So if you have barium chloride, so you have Ba2 plus and Cl minus, so you form BaCl2. If you have potassium oxide, you have K plus and O2 minus, you form K2O. If you have calcium ion with sulfide ions, you form CaS. And finally, if you have aluminium oxide, we have Al3 plus and O3 minus, you form Al2O3. All right. So the way of how we draw the dot and cross, actually no need to be so specific that X is coming from the cation, the dot must be coming from the anion, not that specific. So as long as you fulfill the way of how you are going to fill in the electron, these valence electrons inside an atom, no matter dot or cross, it should be the same, right? Okay, so that is how you are going to represent the ionic compounds in the form of the Lewis structure here. Okay, so what are the factors that are going to influence the strength of the ionic bond? Okay, so ionic compounds usually present as giant ionic crystal lattice. Okay, giant ionic crystal lattice where each of the oppositely charged ion arrange themselves in an orderly manner in three-dimensional array, which explain why ionic compound usually has a high melting point. Okay, so let's say if you have sodium chloride, so they will alternatively arrange themselves in a positive, negative manners so that they'll form a giant ionic network that hold strongly each other via electrostatic attraction forces in this ionic compound. So based on this Coulomb's law or electrostatic forces law between the two oppositely charged objects, strength of the opposite charge can be measured by electrostatic energy, where we say electrostatic energy or lattice energy is directly proportional to the charge, yet inversely proportional to the inter-ionic radius. So in order to have a high lattice energy, you must have a high charge, okay, and small inter-ionic radius. So this is the factors that will measures the strength of the ionic bonds in here generally. Of course, there might be afterwards other factors that comes along together lah. Okay, after we learn more and more about covalent bonding, right? Okay, and here are the three properties of So let's have a look in detail. How does the charge and inter-ionic radius will influence? So generally, we say that greater the charge of the ion, stronger the electrostatic attraction forces between the oppositely charged ion, greater the lattice energy between the ions, and therefore you require energy to break. So for example, if you have lithium fluoride, LiF, and magnesium oxide, now if you look at their inter-ionic radius, they are just different by 3 picometer. Okay, however, because magnesium and oxide ions has Mg2 plus and O2 minus, so the total charge in here will be 4. whereas lithium is made of Li plus and also F minus in here. So their ionic charge in here is 1. So that is why, roughly okay, the difference of the lattice energy in between magnesium oxide and lithium fluoride is almost 4 times differences. Okay, though this formula of Q and the interionic charge over interionic radius in here, it is not a mathematical formula for you to calculate lattice energy. No, it is just a qualitative representations of how we can relate the lattice energy with the oppositely charged ions. Okay, so this is not a calculation; it's more to qualitative comparisons in here. Right. Okay, then the next factor is the interionic radius. So generally, smaller the interionic radius, shorter the distance between the actually it's the nucleus between two ions. So greater the electrostatic attraction forces, higher the lattice energy here. So as you can see, this is a graph of group 1 ions against group 17 ions in here. As you can see, lithium fluoride has the highest lattice energy because it has the smallest interionic radius in between the lithium and also fluoride, whereas rubidium iodide has the highest lattice energy due to it has the highest, largest ionic radius in here. As you can see, the from the graph in here, all right, so the lattice energy progressively decrease with the increase in the ionic radius in here. Okay, so with that, that is the two factors of how you are going to influence the electrostatic energy in between the particles in here. Okay, right. And last but not least, let's have a look at the physical properties of the ionic compounds. It is generally to say that ionic compound mostly has a very high melting point. They have a very high melting point. So why is it that ionic compound usually has a high melting point? Because they have the giant ionic crystal lattice that require high temperature to break the electrostatic attraction forces between the oppositely charged ions inside the molecules in here. Right? So that's why when we describe the melting point of why is it that ionic compound has a high melting point? We just described that because they are ionic compound hold by electrostatic attraction forces between the oppositely charged ion via in the form of giant ionic crystal lattice. So that is how you are going to describe the high melting point of the ionic compound. Now, second is in terms of the electrical conductivity. So most ionic compounds do not conduct electricity in solid state. We are talking about solid state, okay? But do conduct electricity when melted. This is due to, in solid state, you do not have free moving ion. Okay, they do not have free moving ion. Okay, however, as they melted or dissolved in water, so the ions are free to move, therefore can conduct electricity. Okay, so as exemplified in the diagram here, so this is how the ionic compounds looks like when it is in solid. So the ions are not free to move. That's why cannot conduct electricity. But when it is molten, okay, melted, so the ions are free to travel and hence conduct electricity. And same goes to when you dissolve in aqueous ion solution. So you can also conduct electricity in the aqueous states in here. Okay. All right. And last but not least, we have the what we so call hardness and brittleness of the ionic compound. All ionic solid are hard. That means it does not bend. Rigid. That means it does not bend. And brittle, crack easily. Okay, due to the attraction forces that holds in between the ion. So if you have a pressure applied, the ions act like a charge are brought next to each other, and therefore repulsive forces crack the ionic solid in here. What does it mean? Let's say if you forcefully put extra forces in here, so that the whole this lattice shift down. When it shifts down and it has a neutral charge, that is why it will repel and crack easily. Okay. All right. With that, that is the first part of the video of chapter 3 lesson. So hope that you enjoy and I'll see you all in our next lesson. Thank you.